Okay, 6.4 polar coordinate. Okay, we'll learn about polar coordinates. We'll go back and forth between Cartesian and polar. We'll do some equation conversion as well, and find distance with polar coordinates. And mainly this is going to be something you might use in calculus, and that's pretty much the biggest reason we'll do this. But it does simplify some types of problems by using polar coordinate system. Alright, polar coordinates are pretty easy. We're going to start the same way we start with our unit circle with our angles, where we start with standard position being along the x-axis here, east I guess you'd say. And we're going to rotate up by some angle theta, and we're going to go out by some distance r. So our polar coordinates are going to be the points r comma theta, where let's say this is a distance 2 out, and let's say this angle is a degree of 35 degrees or something. We'd say 2 comma 35 degrees. We can do this in radians as well. In fact, most of the time we will do this in radians. Here's a few quick examples then. The first one, I'm going to rotate 30 degrees, pi over 3, and then I'm going to go out 2. So this length would be 2, this angle would be 30 degrees, and the point that I would be at would be right here. Alright, next example, B. I would rotate 3 pi over 4, which we know is over here. I wouldn't go out quite as far, so I'd go out just 1 this time. And it's -1, so I'd actually go back in the opposite direction, -1, this way. So this angle right here is 3 pi over 4, and this length is 1, but I need to go back 1, so I need to go actually the opposite direction to this point right there. And then the last one, I'm going to rotate -45 degrees, so this way, and I'm going to go out a little bit further to 3. So my point is going to be out here. If this is length 3 and this is a 45-degree angle, that would be my point for part C. So here's all the important information, and this is stuff you're going to want to remember. I didn't put this on the formula sheet because it's all stuff that's really self-explanatory. If you just draw a triangle, and you call this x, and you call this y, and you call this r, and this theta, then all these things pop right out. So obviously x is r cosine of theta, because if you do cosine of theta equals adjacent over hypotenuse, multiply both sides by r, you get this. So these all come right from this picture. The Pythagorean theorem gives you this. Tangent is opposite over adjacent. So these are all things that are real self-explanatory right from just drawing a triangle in the first quadrant. So it shouldn't be hard to remember this stuff. So then if you know that stuff, then it's easy to go back and forth between rectangular and polar coordinates either direction, because you can just draw the triangle. So 7 pi over 6 is a 1/6 pi, so this is pi over 6, more than 1 pi, right? So like I said before, if you want to split this up, do the division that you used to do in elementary school. Goes in 1 times 6 is 6. When you subtract, you get 1, so it's 1 and 1/6 pi still. So 1 and 1/6 means you go 1 pi plus a sixth of a pi. And then we go out 2 for the hypotenuse. So it's easy to find x and y using polar coordinates then. You don't have to memorize this stuff above. You can just use this reference triangle right here, where we know that the cosine of pi over 6, in this case, gives us adjacent over hypotenuse, multiply both sides by 2. If you do that in your calculator, you get x equals about 1.73. Make sure you're in radian mode. And that's going to have to be negative because we're going back in that direction. And then I can find y as well by doing the same type of thing. I can do sine this time. Sine of pi over 6 is equal to opposite over hypotenuse. Multiply both sides by 2. And the 2's cancel. 2 times the sine of pi over 6 in radian mode gives us 1. Now we know that needs to be -1 as well because we're going down here. So I have -1.73 comma -1 as in the rectangular coordinates. Now if I wanted exact rectangular coordinates, I could do that as well, because we know this is a special right triangle. This is a 30, 60, 90. So whatever this side is, the small side, this is always twice that, and this is always that small side times the square root of 3. So what that means is y is 1, as we found out. Right from here, if this is 1, make this hypotenuse 2, which works out. So therefore this is just the square root of 3. So this number right here is really just negative square root of 3 comma -1 from our special right triangles. That's a better way to represent the answer. Okay, let's go back the other direction now and find polar coordinates for rectangular coordinates. So I'm going to graph the point 1, -1, which is right here. We want to find 2. So There's different ways to get this answer. We can rotate any direction we want, but let's rotate positive first. Let's rotate all the way around. Obviously we know this is a 45-degree angle right here, so let's rotate all the way around in the positive direction, 315. So if we go all the way around 315, and then we can go out the length of this hypotenuse. Now if you look at this as a special right triangle, this is 1, 1, and this has to be 1 square root of 2. I'm sorry, square root of 2. If you use your special right triangles for your 45, 45, 90. So basically that means that my answer is square root of 2 comma 315 degrees in polar coordinates. Now we can do that differently, so if we want we could use radians for this. I'm going to stay in degrees for now, but I also can do, there's several different ways to get this answer. Another way would be to write negative 45 for my angle and square root of 2 for my my length going out. That would rotate me this way, negative 45 to the same spot, and I would go out square root of 2 still to get to this point. Another thing I could do is rotate this way to 3 pi over 4 or 135 degrees, and then just go back negative square root of 2. That would work as well, because that would take me back this way to this point right here. So there's different ways to do it, infinite ways we can represent the answer, but there's a few. Okay, when we convert then from polar coordinates to rectangular form with our functions, so now we have a function that's in polar form, where we have r varying with theta. And you can graph this in your calculator in polar mode if you want to see what it looks like, but we can convert it algebraically as well. If we make this negative 2 divided by the sine of theta, that's cosecant really 1 over sine, we can multiply both sides by the sine of theta, and that gives us negative 2. Now you might remember that this is right here. Y is r sine of theta, x is r cosine of theta. So we can use these relationships right here to convert back and forth in polar to rectangular and vice versa when we're dealing with functions. So we're going to use this one right here. Y is just r sine of theta, which is exactly what we have right here. So that's just y equals negative 2. And so what we should expect to see is a line that is horizontal and that goes through negative 2. And that's exactly what we get if we graph this in our calculator in polar mode. Okay, this one's a little bit tougher. This is a circle obviously, but we want to go back the other way and convert it into polar form. What we can do is FOIL this out and look for x squared plus y squared, because we know that r squared equals x squared plus y squared according to our triangle that we drew, where this was x, this was y, and this was r. The Pythagorean theorem gives us this relationship. So we can FOIL this out and look for that x squared y squared and replace it with r. So this becomes x squared minus 4x plus 4, and this becomes y squared minus 6x plus 9 equals 13. Now let's get that x squared plus y squared together, and then we still have the negative 4x, and I'll add the numbers together as well now. 4 plus 9 is 13, and I still have the this should have been a y right here, so the negative 6y equals 13. Okay, we can then replace this with r squared. These cancel, subtract 13 from both sides, and I'm going to replace x. I know that x is equal to r cosine of theta. I know that y is equal to r sine of theta, right from our triangle once again that we put in the first quadrant, where this is x, this is y, and this is r. This is theta. You get these relationships right here as well, like we talked about. So I'm going to replace x with r cosine of theta, because I'm trying to get rid of all x and y's to put it into polar form. Y is r sine of theta equals 0. I'm going to factor out an r, and I get r minus 4 cosine of theta minus 6 sine of theta equals 0. So I get two things. I could set r equal to 0. That doesn't help me at all. That's not going to give me anything of use. But I could set this equal to 0 to solve this equation. And when I then set it equal to 0, move these things over to the right side, I get r equals 4 cosine of theta plus 6 sine of theta. And that would do just wonderful. If I graph this, what I see is a circle with a radius of the square root of 13 centered at 2, 3. So you can go ahead and graph that in polar form in your calculator. In fact, why don't we do that really quick? Go to mode in your calculator, and we want to go polar this time. So we're scrolling down to function mode, and we're going over to polar mode, hit enter. Now when we go to y equals, what we're going to see is r, and we want to type in what we had, which is 4 cosine of theta plus 6 sine. And you just use X for the variable and theta will automatically pop in. We might have to change our window, but if you hit graph, you're actually going to see this. It looks more like an ellipse, but it's actually a circle. It's just that my viewing window, my rectangle, you can tell these is rectangular, you know, where these coordinates are spaced out a little bit more than the y coordinates. But it is centered at 2, 3 like we thought, and it does have a radius of the square root of 13. It is a circle. And in fact, I can make this bigger and make it more of a rectangle and show you that when you space these x and y coordinates out the same distance, you do get that circle that we were talking about. Alright, let's try some of the homework problems and see if we can get better at this.